Arun sir?
Yes, sir. Good evening. Shall we start?
Yes, sir. Sir,
Okay.
we can start, sir.
Yes, sir, please. Good evening to everyone. It's my pleasure to invite you all for the weekly online lecture series, Webinar 59, an engineer's talk being organized in commemoration of its 30th anniversary celebrations of IEI Salem Local Center. I would like to request the chairman of IEI Salem Local Center to welcome everyone. Please, sir.
Thank you, sir. Respected today's chief guest and keynote speaker, Engineer D. Kotaya, sir. Our beloved Honorary Secretary, Dr. C. Domini, ma'am. Engineer Armugam, sir. Esteemed members of IEI Salem Local Center and Tamil Nadu State Center. Our Sonaraj, sir.
Good morning, sir.
Partner institutions, organizing team, participants, students, our IEI office staff, Mr. Tiago, and friends. A warm welcome to each one of you to this special lecture session organized by the Institution of Engineers India, Salem Local Center. This occasion is part of our ongoing celebration of the 30th anniversary of IEI Salem Local Center and our widely appreciated Engineers Talk webinar series. It gives me immense pleasure to greet each one of you as we continue to foster knowledge sharing and meaningful discussions that shape the engineering landscape. Our organizing team, led by the engineers Dr. R. Satish Kumar sir, Dr. A. Kumarvel sir, Engineer K. Selvam sir, and Engineer Aruman sir, has curated a year-long series of impactful events. Today's session, Webinar 59, is no exception, offering us insights into a highly relevant and specialized topic. I extend my heartfelt thanks to our distinguished chief guest and keynote speaker of today's special session, Engineer T. Kotaya sir, Assistant Professor of Mining Engineering, University College of Engineering, Kakatiya University, Kudangulam. Sir, we are honored by your presence and eagerly look forward to your address on the topic behavior of coal mine roof during deep learning operations. This topic holds immense significance for the mining community and the broader engineering fraternity. We are privileged to have a diverse audience of professionals, academicians, students, and enthusiasts join us today. Your participation exemplifies the spirit of engineering, a commitment to innovation, learning, and collective growth. I take this opportunity to express our gratitude to the IA Mining Division Board for their support in organizing this special lecture. Also, I request all the our today's participants, please keep your microphone muted during the session. Use the chat feature for questions which will be addressed during the Q&A segment. As we embark on today's enriching session, let us actively engage and make the most of this opportunity to learn and grow together. On this festival day, as we celebrate Christmas and prepare to welcome the new year 2025, I extend my heartfelt greetings and best wishes to each one of you. Thank you for joining us and supporting this event amidst the festival season. Without further ado, once again, I thank you all for joining today, even though, as I already mentioned, it's a festival day, festival week. Thank you for joining. and I wishing all an insightful and rewarding session ahead. Thank you. Jai Hind.
Thank you, sir, for welcoming everyone. Now it's my pleasure and privilege to introduce Engineer D. Kotaya, Assistant Professor in Mining Engineering, University College of Engineering, Kakatiya University, Kothagudam. Engineer D. Kotaya holds dual BTech degrees in Computer Science and Engineering and Mining, and also dual MTech degrees in Computer Science and Engineering and Mining. He also had qualified at GATE twice at 2009 and again in the year 2012. Further, he is pursuing his doctoral degree at National Institute of Technology, Raipur. He has expertise on both computer science and engineering and mining engineering. He is enthusiastic about learning new concepts in emerging technology. He has a wide work experience on both the field of engineering, on both hands-on and the teaching. He has been guiding projects for BTech and MTech. He has filed application for a patent for designing soil testing device integrated with IoT. He has attended various faculty development programs and being involved in conducting various academic programs and workshops. He is also member in various professional bodies and contributing his responsibility through them to the society. With these words of introduction, I would like to invite Engineer D. Kotaya to deliver his lecture on the topic Behavior of Coal Mine Roof During Depillaring Operations. Over to Engineer D. Kotaya, please, sir.
So, very good evening to one and all. So, myself, D. Kotaya, working as assistant professor in the University College of Engineering, Kakatiya University. May I audible, sir?
Yes, sir, audible, sir.
So, firstly, I would like to thank the IEI Local Center, Salem, Chairman Sri Tangaraju, sir, Dr. Tangaraju, sir, and Dr. Dhaumani, madam, and my student and colleague Swarna Raj and the engineers team of the IEI Local Center. So it's a great pleasure to give you a session on this on the ages of mining engineering division. So today's my topic is roof behavior of coal roof during the depillaring operations. So shall I start my presentation, sir?
Yes, sir.
Is it visible to you, sir?
The screen is not visible, sir.
Yes, sir, not visible, sir.
Right now, ma'am?
Yeah, now visible, sir.
Visible, sir.
So, as of you all know, day by day the population is increasing. So, simultaneously, if the population is increasing, means definitely we have the energy resources, the consumption of the energy is also increasing. So, if you want to fulfill the requirements of the uh, population, definitely we have to go for the innovative technologies and the mass production technologies. So, presently, so we are having we don't have any manual quarrying or manual processing, and right now we are having only two processes. One is semi-mechanized method and other one is the fully mechanized method. So but in the case of semi-mechanized method, so we are extracting the mineral up to a limited depth only, but if you are using if you are extracting the mineral by if you are extracting the mineral by fully mechanized method, either it may be through CM, continuous miner, or the shearer in long wall cases, and the investment cost towards that projects are very high. But ultimately, at last, definitely we have, at last, the profit is the important factor or the socio-economic factor in the mining area. So this is the case where I have done one scientific study based on this topic. So this is this presents from 2013 to 2019. So these are the fatality ratios in underground mine, especially most of the accidents are occurred due to roof fall and side fall. So these are the statistics from 2013 to 2019. So below ground, as for in 2013, so below ground is 19, total are 77, and fatal accidents due to roof and side falls are 10, and below ground in total number of serious accidents and serious accidents due to the roof and side falls. So these are the statistics 2013, 14, 15, 16, 17, 18, and 19. So day by day, in olden days, we are not having any monitoring strategy for extracting the coal. But right now we are having each and everything will be automated, fully automated mines are available in Singareni Collieries, just like ALP, Adriala Longwall project. But investment cost towards the project is very high. Definitely we have to consider the cost. So these are the statistics based on the DGMS report I have taken. So for this specialized topic, I have selected one case study, and myself only done this study in, this is the oldest mine in Singareni. Britishers have started this mine. So the mine name is 21 Incline, and this mine is located at Bhadratri, Kottagudem, Telangana state. And this mine is having 4 seams: index 1, index 2, Queen seam and King seam, twin seams. So the basic geology and geomining conditions of the seams are, so all the whatever the panels we are having, the upper panel that is index seam 1, and the king seam, bottom seam is the king seam. The both seams are extracted, and whatever the queen seam we are having, they are proposing the queen seam for extracting the thick seam mining. That is almost 10-meter seam is having at that location. So for that, we have conducted one study, and we have collected all the field data, and we have done the numerical modeling, and we have compared all the information regarding the field data and the numerical modeling, and we have designed the safety factor, and we have taken the material properties, and we have taken the rock mass ratings. All the information we have gathered, and we have prepared a model for this queen seam. So these are the details of the mine, where the panel name is MM9A panel, and the gradient of the panel is 1 in 12, and the details of the MM9A panel are in under the table. So this is the borehole or lithology of that particular mine. So the gray sand or sandstone, that is the index 1 seam. The seam is caved out or bowed out panel, and the next one is the top section partially developed with the sandstone on pillar parting after depillaring, and whatever the bottom seam we are having, that is shale and coal. So these are the details of the MM9A panel. The area of the complete panel is 33,729 square meters, and the panel length is 255.71, and the panel width is 131.90 meters. Number of pillars in that panels are 33, and the pillar size is 34.17 into 33.24 center to center. And the minimum depth is 148.96 meter, maximum depth is 164.11 meters. And the height of the extraction is 4 meters, and the width of the split or slice is 4.2, and the width of the out by is 3, and in by is 3, out by is 2 meters, and maximum width of the diagonal length is 190 meters, gradient is 1 in 12. So why I am quoting all the parameters means, so while we are considering the roof stability or the supports design of the particular roof, definitely we have to consider panel length, pillar size, panel size, height of the extraction, depth of the cover, and what is the superimposed strata or overlaying strata on the particular seam. So definitely we have to consider all these parameters, then only we can design a support system or else stability system, or else we can draw the safety factor for that particular panel. So this is all of you know the pressure loss theory. So directly strata behavior mechanism in that pressure of series, simply we are extracting a web cut on that particular solid material, and whatever the remaining forces we are having, the forces are redirected into a particular direction. So that is either it may be a front abutment load or back abutment load or both side of the abutment loads. So that means if you are extracting the mineral on a particular seam, so automatically, definitely we have to provide a passive support or active support for safe extraction of that material. So if the material, if the roof and the floor are both are the strong behavior, then if the floor is strong, then automatically in the case of roof, definitely the whatever the roof we are having, the roof is sagged. If the roof is strong, then automatically we are having a heaving problem. Both roof and floor are strong, and automatically the load will be directed into a pillar, and that is nothing but the bulging factor. So based on this strata behavior or pressure or theory, we are categorizing three types of roof bolting theories, that is keystone theory and suspension theory and pressure or beam theory. So based on these three theories, so what is the immediate roof, and that is considered up to 6 meters, and what is the immediate floor, that is up to considered up to 3 meters, and what is self-supporting roofs based on the site conditions or the geomining parameters, we are installing the roof bolts. So these are the strata failure scenarios are the blueprints. So first one is the tension, joints, faults. So majorly faults are definitely faults or dikes or discontinuities or any shear zone or weak zone at that particular strata. So why? Because if you are extracting the mineral means definitely there is a heterogeneous types of roofs are available at that particular site. So based on the lithology or whatever the exploration data we are collecting at mines at initial stage of mining. So if roof has coal, so there is no need of worry. If the roof has sandstone, so definitely we have to provide definitely we have to care about the roof. And if the roof has a shale, at that time also definitely we have to take care. And if the roof has dirt band or rock stone, so this is the critical case, leave the coal patch up to 0.6 meter, and we have to provide extra supports to at that particular cavity, at that particular point. So why? Because according to the RMR, so we are classifying the roofs as poor, very poor, fair, good, excellent. So only from fair range only we are selecting the extraction strategy. Otherwise, poor or very poor we are not considering. Why? Because more number of supports are more number of supports are required for that particular area. So these are the factors influencing the strata behavior. So that is span, that means exposed area of that particular area. In situ stress. So in situ stress means that is the pre-mining stress. So that means before that, whatever the stress we are having, the stress is already stored at the time of formation, and the induced stress, that is the post mining stress. So once we are disturbing the stored in that seam, those are directly redirected to the surrounding area, and the shape of the profile and the physiomechanical properties of that particular mine site. So physiomechanical properties means porosity, permeability, the Young's modulus, poisonous ratio. So these are the parameters are important for extracting any thick seam mining or any underground seams. So and major mining parameters and strata control are depth of the seam, layout of the face, method of treatment of the GOF. Method of treatment of the GOF in the sense, so we are extracting the mineral by caving or we are extracting the mineral by stowing. So definitely, if the roof is not in a good condition, definitely we have to extract the mineral by stowing method only, and we are not preferring the caving method. And the working thickness of the coal seam also the major parameter in the extraction process. So these are the critical parameters for control study. So one is a constant parameter and the other one is the variable parameter. So constant parameters means these parameters are already site specific, or uh, whatever where we are extracting the mining, that is material properties or geomining conditions or geological conditions or any tectonic activities are occurred at that particular site. So those parameters are comes under the constant parameters. So just like geomining condition, virgin seam, in situ stress, rack mass classification, all are comes under depillaring the panel. At the time, these type of parameters are comes into the picture. So those are stress, deformation, bed separation, load on support. So these are the other available parameters. The parameters are dynamically changing while extracting the or while depillaring the panel. So these are the details we are collected in the field. So MMA 9 panel seam consists of 33 pillars bounded between north 7 dip of 50.
Yes, sir. Audible, sir.
So these are the details we are collected at the field. So the length of the panel are 134 meters and 250 meters, and the MMA 9 parallel seam. And the MMA 9 parallel is a Queen seam, the index seam 1, Queen seam, king seam. And in between that one seam is we are having that seam is extracted by blasting gallery method. So right now DGMS is not giving any permission for the blasting gallery method. Why? Because in the case of blasting gallery method, area of exposure is very high, and if the complete area of exposure is high, means there is a chance of air blast or the accumulation of the poisonous gases or accumulation of the water. So due to these parameters, DGM is not approving the blasting gallery method, not giving the permission to the blasting gallery method. So this is the mine plan where we are conducted the study. So MMA 9 panel of kin seam. So in map we are showing that MMA 9A panel. This is the zoomed view of that particular panel. These are the pillars how we are developed. And this is the offset plan of that particular MM9A panel. And these are the developed pillars. So parting between the bottom and top sections. So if you are extracting the mineral by slices means according to the DGMS or CMR provision, definitely the parting should not be less than 3 meters. Then only we can extract the mineral. Otherwise, there is a chance of major collapse in that particular area. So initially a panel is developed with the gallery size of 4.2 meters and the 3 meters height. So normally in mining conditions, height is 3 meters and the width of that particular gallery is 4.8 meters. So the minimum of 1 meter parting is observed at that 1 DS. In field visit, we have observed that. So in 1 DS of 52 level and the 2 DS of 52 level, so the parting between the seams is only 1 meter. And the middle of the galleries, the parting is found to be lesser than 1 meter, especially in 1DN 51 level and 1DS 51L. So these are the values observed and collected from the mine management. So this is the parting between bottom and top sections at these junctions. So all the statistics that we have taken, all the values are collected from the mine management. So 51 level, 52 level, 53 level, 55 level, and 55 AL level. And these are the 6, 5, 4, 3, 2, 1, 1DS, 2DS, and 3DS. So these are the parting in between the two seams: 3.60, 3.95, 3.98, 1.80, 1.90, 2 meters, 3.10, and the 1.80. And the 52 level, 3.15, 3.65, 3.35. So these are like this. We are having the parting in between the two seams, and the roof condition of that particular panels are during the field visit of the MM9A panel. Roof conditions of various parts of the MMA9 panel studies. It is observed that the most of the galleries of roofs are spalling, hanging roof, hanging supports, and the meshes are swelling of fillets. The conditions of the galleries at critical locations as mentioned below. Almost all the dip galleries of this panel have been developed cracks in the roof. The fracture due to development of high stress concentration, which tends to roof fail due to this. The height is to 3.3 meter. So these are some pictures I have taken from the uh, 21 incline mine. So the roof shows that the fractured roof, and whatever the roof we are having, the roof is protected by the W straps. And in this diagram we have shown these are the cracks, major cracks in the roof. So this shows that there is no protection in the roof, and this is the danger sign of the mining. So these are the cracks. Due to the cracks, the height is increased, and in between the cracks, we are installed already. The mine management installed the W straps. So this is the fractured roof in the 51 level, and this is also the fractured roof in the same level. So by the above picture, so one DS to 2DS as mentioned above, MM9A palace surrounded with the gold panel in north, south, and dip sides. So all the surrounding panels are excavated, and there is no stubbing process in that extracted panels. So that's why whatever the load we are having, the load is applied towards the downward direction, that is on the quincy. And the next, the 51 to 52 galleries roof layer of 3.3 meter detected from the 51 to 52. After the detached block, the roof is supported with the mesh and roof bolts with the strap to prevent fall of roof. Already how we have shown in the figure. So these are the height of the roof fall height is 2.7 meter, and the gallery height is 5 meters. According to the coal mine regulation, or according to the stipulation of the DGMS, so normally the height of the extraction is up to 3 meters. So if you are using the fully mechanized mines, means there is a maximum height is up to 5 meters. But here we have observed that the roof fall height is 2.7 meters and the gallery height is 5.5 meters. So complete height of the gallery is 7 to 8 meters, and the length of the roof wall is up to 15 meters. So these are the material properties we have collected from the mine management for developing a numerical modeling. So coal, the compressive strength and tensile strength and modulus of velocity and rock mass rating. So coal compressive strength is 28 to 32 MPa, and the tensile strength is 2.5 to 2.8, and the modulus of velocity is 5, and the rock mass rating is 40. And sandstone is 40 to 45, the tensile strength is 3.5 to 4. And the modulus of velocity is 10, and the RMR is 60. So I previously told that, so RMR, rock mass classification, while we are extracting the mineral, we are extracting the seam, definitely we have to consider the rock mass rating. If the rock mass rating is fair, then only we are extracting the mineral, and we are not extracting the mineral at the case of poor or very poor. So these are the conditions of the top section panel. The top section panel has 30 pillars just above the MM9A panel, and it is already showed in the map, and all the 30 pillars top sections are almost exactly superimposed of the pillar of 9A panel. So the superimposed of the panel means the load on that particular proposed panel is very high, and it is situated, it's 4 meter above the 9A panel. The top section galleries are not supported with any support system. The index seam has already gone out panel, and during the inspection it is also from management that parting of 9.1 between top section roof and index seam had many local falls and few major falls. The falls occurred in 55 level from 5D to 7D, and the 5D from 554 level to 55 levels are the major falls. Due to these, cracks extended from index seam to the top section and top section of 9A panel. As a result, the roof sides and pillars of 9A panels are yielding. If the depillering operation commences in the 9A panel, this excavation activity will enhance the high stress concentration, cracks development, weakening, and deterioration of the roof, and reduce the roof safety factor and requirement high support system. And this is the major drawback. At a dip side, the sump is at the right side. The Quinsim has a sump of 3 lakhs gallon capacity situated up to 47 level to 1D to 3D in rise section. The seepage of water from the rise working and old workings of King Seam are being collected in the sump. So 75 HP submersible pump is used to pump the water from the sump of King Seam to the Queen Seam. So two multi-stage centrifugal pumps of 190 HP at 2D and 3D of the 47 level are used for pumping the water to surface filled bed. As the pump is situated in the right side of the panel, the water pump from surface. So as I already told that physio-mechanical properties of the rock in that. So if the sump is at right side, so there is a chance of permeability or porosity. Through the permeability or porosity, the water passes to the proposed area, or through the cracks, or through the discontinuities, or through the fracture zones, or through the weak zone, there is a chance of passing the water to the proposed panel. So based on all these details, we have conducted the numerical modeling for this case. The detailed field investigation is carried out, and the rock mass properties of mine site are also collected to carry out the study for depillering of 9A panel of Kinsim with caving method. For the three-dimensional finite element analysis performed completed the study by ANSYS software. Three-dimensional finite element models have been developed to analyze the stress and displacement distribution around the pillar and gallery, and for the estimation of the safety factor of the pillar and the gallery. For the development of the three-dimensional numerical model, pole seams, top section development, bottom section depillering, and other coal-bearing strata, that is overlaying strata, or superimposed of strata, or simply we can say the depth of the cover, that is the depth from surface to the particular proposed area, or a model based on lithology of the mine site are performed the stability analysis of 9A panel. A total of 3 numbers of 3D finite element models have been developed, out of which one model is in situ and other models are excavated model for development and depillering of bottom section. As discussed above, the height of the gallery is increased to 4 meters due to spalling of the roof. However, the height of the gallery in bottom section is considered as 3 meters uniformly. So this is the lithology used for the finite element model. So index 2 seam is 2.29 meters and 3.2 meters. That is the part slices in between the index 2. Index 1 is 2.6. And whatever the queen seam we are having, that is 9. This queen seam, that is 9.5 meter. So we have to extract the proposed seam is queen seam, that is 9.5 meters. But the finite element model of 9A panel for depillering operations, as we discussed above, all the out of the total, the coal seam of 10 meter thick seam is located 3-dimensional average depth of 150 from the surface. Out of this, 10 meter top section is developed with 3 meters height, and the bottom section height with a parting of 4 meter thick seam, 2 sections. The bottom section is developed with a in the roof of the top section. The average size of the pillar is 34 meters from center to center, and the gallery width is 4.2 meters. The bottom and top section consist of 140 pillars, 70 for bottom section and rest 70 for section of the 70 pillars, and 10 and 7 pillars are developed along the strike and dip direction respectively. And the 30 pillar outside of the panel are left as barrier. So if you are extracting the mineral by slicing or by stooking, definitely according to the coal mine regulation or the DGMS statutory, we have to leave the rib as 2 meters. So then only we can extract the panel. The size of the model is 84.2 meters into 844.2 meters into 742.2 into 201.26 meter. All these are the dimensions of that particular gallery. All the galleries including split and maintained with the 4.2 meters width, and the bottom figures, all the details are explained in the bottom figure. During the depillaring operation, each pillar is extracted with 4 slices of 4.2 meters. So whatever the seam we are having, the seam is maybe extracted through slice or through stooking. So through slice means the first slice is in by slice. So at that situation, we are considering some amount of extraction. And at the time of last slice, that is out by slice. So whatever the judicial extraction we are having, that is maximum amount of mineral will be extracted. So this is the finite element model of MM9A panel. So these are the dimension. So in that we are showing strike or level and the dip direction. So these are the dimension of that particular MM9A panel. These are top section clean seam. So these are the pillars. These are the developed pillars for extraction. So these are the barrier pillars, bottom section debuilding of kinseam of MM9A panel, and these are the slices shown in the picture. And for connection of the numerical modeling technique, we have considered the rock mass properties used for the finite element model. So coal modulus of velocity, poisonous ratio, and density are overlaying strata, or the mass of that particular, or the load or mass or density. So coal is 2, poisonous ratio 0.3, and the 1400 kg per meter cube. And sandstone is 5, and 0.05, 2500. Goaf is 0.6, 0.1, and 2000. So generation of finite element mesh model, the finite excavation models are produces these number of nodes, and coarse mesh is developed in the coal bearing strata away from the mining affected zones or shear zones or crack zones. So these are the finer mesh and the top section pillars, and these are the finer mesh slices and ribs. So all 3D finite element models have been analyzed using the elastic behavior of rock minerals. The result of the vertical stress, principal stress distribution, and vertical displacement distribution, the factor of the safety, and MMA9A panel along the considered path and the coal seam partitions are presented. Vertical stress distribution is in that figure we have shown, we have plotted a graph depict the vertical stress distribution profile of MM9A panel. The vertical stress varies between 0.5 MPa to 20.5 MPa. It is also observed that development of vertical stress is lesser at the center of the pillar, and it is towards the corner of the pillar as shown in the figure. The depilling, the depillared pillars of ribs may be experienced a vertical stress of 0.5 to 1.5 MPa. However, the split experience the vertical stress of 3 MPa. So these are the extracted pillars, and what are the bottom pillars we are having? These are the pillars to be extracted, and these are already extracted pillar. So this is the pillar, and this shows the stress distribution around the pillar. So this is the top view of that pillar. So in center there is no stress on the pillar, and if the pillar is moving towards the corner of the pillar, the stress is more. So this is the vertical stress distribution 0.5 meter above the roof of the bottom section, and he observed that the split area and developed pillars, and what are the barrier pillars, and what is the panel, and what so the graph is plotted in between vertical stress and distance. And the vertical displacement distribution, the vertical distribution profile is estimated along the considered path of IEI section. So it is already shown in the figure. And the vertical displacement is observed between 35 mm and 42 mm in the groove, and 23 to 25 mm may occur in the pillar. However, 26 mm is observed in the split gallery. So these are the principal stresses distribution. So first one is the major principal stress, and the second one is the minor principal stress. So in the case of major principal stress or minor principal stress, the stress acting on the pillar, the center of the pillar is less, and towards the corner of the pillar, the principal major or minor principal stresses are very high. So this is the principal stress distribution profile in the roof of the bottom section. So whatever the zone we are having, this is the tensile zone. So this is the as expected, the minor principal stress is tension is the entire GOF area is compressing in the split and gallery. The minimum major principal stress may be developed in the GOF and maximum occur in the excavation. So for this we have designed the safety factor of that particular gallery and the roof. So by using this formula, we are deriving the safety factor. So in general, safety factor of the pillar or gallery or any location enhanced with the increase in GSI RMR of coal strata and dimension of the pillar. So according to coal mine regulation or DGMS statutory, with water or without water, always safety factor should not be less than 1.5. So if the safety factor is 1.5 means definitely we have to take care. If the safety factor is above the 1.5, then only we can go for the extraction. The roof of the bottom section, the major and minor principal stresses are extracted in the junctions along the path A dash. This is the sectional view of that particular plan. The junctions are considered and critical locations since high load concentration may be developed, and all the details are displayed in the table. And it is reported that all the 5 critical locations may yield due to the tension proper supporting system of roof bolts, W strap or cable bolts which must be installed to stabilize the roof. So the safety factor of roof of MM9A panel. So minor principal stresses, major principal stresses, and the safety factor. So in the case of first case, there is no safety factor. So only in third case, the safe factor of safety is only 0.38. But according to the DGMS or according to the coal mine regulation, the safety factor is definitely above 1.5. So we have observed all the cases, the height of the roof, mineral principal stresses, major principal stresses, and the safety factor. So all the cases we have prepared. So there is no safety factor available at that particular location. So 0.24, 0.36, 0.49, 0.64, 0.69, 0.84, and 1.10. This is the highest safety factor. So while we are considering the 4-meter thick coal, and the above, the safety factor of the MM9A panel is here we are considering only 3 meters thick coal. So if you are considering 3 meters, there is no safety factor, only the 0.38 is available, and remaining cases all the tensile failure. And while we are considering the 4-meter thick coal, so only the highest value is 1.10. So based on all these numerical modeling, field visit, the depillaring of caving MM9A panel Quincy bottom section number 21 incline mine Illandu area SCCL is conducted based on field investigation and numerical modeling analysis. So MM9A panel is developed with 3 meters height in bottom section with sandstone floor in Quincy. The top section and is developed with the height of 2.5 meters and exactly superimpose the pillar of MM9A panel. Also, index seam has a gored out panel which is 9.1 meter above the queen seam of the top section roof. MM9A panel has a gored out panel in the 3 sides such as 18B north and BZ5B and the MM5A deep panels and developed pillars in the right side. Minimum parting between The minimum parting between bottom and top section is observed as 1 meter at the 52 level of the 1ds, and the junctions, however, the maximum parting is observed as 4 meters at 6dm and 55 AL junction. The galleries between 1ds and 2ds of 51L, 52L, 53L, 55L, and 55AL are mostly heavily fractured roof, and the height of the fractured distance is almost up to 2.5 meters, and the fractured roof is up to 5 meters. From the numerical modeling result, the vertical stresses ranges between 0.5 MPa to 20.5 MPa. Maximum vertical stress 20 MPa is developed on the barrier pillar and split pillar may be experiences. And the maximum and minimal vertical displacement may occur between 35 mm and 42 mm in the gove to 25 mm may occur in the barrier pillar. However, 26 mm occur in split gallery. Safety factor of the roof of the gallery of the panel are estimated at various critical locations or junctions or split level between 53 level and 55 level. All the critical locations may be experience high tension load, hence all the locations are yield due to tension. The top section panel has no support installed in the roof. This panel has highly distributed for the parting between top section and index seam. Many falls are observed in the top section. The falls occurred in the 55 level from 5D to 7D and at 5D from 54 level to 55 level are the major falls. Due to this, the cracks are developed from index seam to the top section and top section of MM9A panel. Hence, majority of the galleries of MM9A panel have seen with the cracks, bends in W straps of roof bolts and yielding of the roof layer. Safety factor of the coal parting between bottom and top sections of the panel are estimated from bottom section to the floor of the section. It is observed that safety factor of the pillar till 3.5 meter height, when the 4 meter height, it is lesser than 1 and the heavy nearly 1 for a roof layer between 3.5 meter and 4 meter height. Based on the field study and the numerical modeling study, it is conducted that the extraction of coal from the 9A panel of Kinsim bottom section with repillaring by caving method may not be possible. So this is the case we are taken in 21 incline, and we have studied, we have collected the field details, and we have conducted the numerical modeling. By all the variants and comparison, there is no chance of extracting the may not be possible for extracting the Kinsim. The major drawbacks in this area is the height of the major problems in the extraction of the Kinsim is the overriding or premature collapse in the pillars, and the height of the extraction is more, and the fractured in the particular zone, and the roof is the coal is exposed. We are left for the lifting the coal for barrier pillar. The coal is exposed to spontaneous heating. That is one of the case. So these are the parameters. These are the major issues in the behavior of roof, or the major parameters where we are extracting the coal or depillaring the panel. So thank you, sir. Thank you very much. Any queries?
So thanks a lot, sir. Wonderful explanation. Yeah, very good session, sir.
Okay, so if there is no query, means shall we conclude, sir?
Yeah, sure,
yes,
sir.
sir.
Yes,
You
then
can text also. If any queries are there, you can directly text or WhatsApp, or you can mail, or you can WhatsApp.
okay, sir. Okay, sir. Well, sir, thank you. Thank you very much for your detailed presentation on behavior of coal mine roof during depillaring operations. Now, I would like to request the Honorary Secretary of IEI Salem Local Center to propose vote of thanks. Ma'am, please.
Okay, sir. Thank you, sir. Audible answer?
Yes, ma'am, you are audible.
Most respected our chief guest and keynote speaker, Engineer D. Kotaya, sir. Our most respected chairman, Dr. K. Thangaraj, sir. Respected committee members, council members, Mr. Arumugam sir, Mr. Thiagu. Good evening to all. It's my privilege and honor to propose vote of thanks in this great occasion of Engineers Talk, a weekly online lecture series. This is the 59th webinar series. The topic is behavior of coal mine roof due de-pillaring operations. Actually, it is very important topic for mechanical engineers. So on behalf of IEI Salem Local Center, I would like to express my heartfelt gratitude to our chief guest and keynote speaker, Engineer D. Koteya sir. Sir is Assistant Professor, Mining Engineering, University College of Engineering, Kakatiya University, Kotagunda. Sir, my sincere thanks for your exceptional information about this. Your insight have significantly enhanced our understanding of this critical topic. Your contribution are vital for enhancing our knowledge in this field. Let us continue to learn towards safety and more efficient mining practices. So my sincere thanks to our beloved chairman, Dr. K. Tangaraj sir. Sir is always dedicative chairman for all our IEA activities. Thank you, sir. I would like also like to extend my gratitude to our engineers talk team series, Dr. R. Satish Kumar sir, Dr. A. Kumaravel sir, Engineer N. Arumugam sir, and Engineer K. S. Elvam sir for their support always. I would like to thank the special thanks to Engineer N. Arumugam sir for his wholehearted support throughout the event. I would like to express my appreciation to Mr. Thiago for his hard work and dedication in making this event a success. I also wish to express my gratitude to all the council members, students for their kind attention to make this event very fruitful. I also appreciate the participation of all the attendees. Thank you once again. Thank you, each and everyone.